Hi, everybody. Thank you for your patience and for tuning in to our almost last seminar of the semester. I'm not going to take a lot of time, but really happy to introduce Martha Buckwalter Davis, who did her undergraduate degree here at Alfred and graduated in 2006. Worked with me for a couple of summers in the Adirondacks, which was great. Went on to get a master's degree in geochemistry from Queen's University. And now she and her family live in Ireland, and she works for Golder. I never remember if it's Golder or Colder. Golder. And she'll tell you more about that. So I'm just going to turn it over to her.
Did Nicole start the recording? Yes. Just gonna put my mic on here. Okay. Thank you very much. So I'm going to try to start this. And that is all on. Oh, go to, okay. Oh, yeah, okay.
Just click on share.
Yep. Okay, let me know if that works then. Is that showing up on Zoom, Fred? It is. Come through on Zoom, the presentation and no notes? Okay, very good. So, sorry, I'll start from the beginning here. Thank you so much for listening in on Zoom and here in person. Hope you can hear me okay, and be very happy to answer questions at the end of the presentation. So today I'm talking about a project that I did in my work as an environmental consultant. So yeah, my title's geochemist, but I do a lot of different, like many consultants, I wear a lot of different hats for different projects. So this project allowed our client to generate recycled concrete aggregates. So this project was completed in Ireland in accordance with European legislation. So I'm going to kind of go through that legislative framework a little bit. You know, not because it's applicable to you, but because it's a part of how the project went on. And I think what's interesting about this project is demonstrating sort of environmental protection and looking at these overall sort of recycling projects, reducing waste, sustainability benefits, and things like that. So I was very fortunate to grow up in Alfred. I knew from a very young age that I wanted to be a geologist. I think age 8, we had a creek behind our house that I played in, and really loved that, especially an interest in water and rock interactions. I had originally intended to study hydrogeology for graduate school, but after I left Alfred with a bachelor's in geology and environmental studies, I lived and worked in Canada for a while my husband was doing grad school. And that led me to geochemistry, and I did my master's at Queen's University in Kingston, Ontario, not Kingston, New York. So my master's, I was looking at mine tailings, and then there's a very old picture of me in the digging holes in the Adirondacks with Michelle. So as an environmental consultant, maybe someday you will, when you finish school here, you'll become an environmental consultant. It is project-based work. So that project-based work starts with a problem. And in this case, for our client in Ireland that owns a landfill, their problem is that there's a construction boom in Ireland right now. They are a landfill that is a former quarry, so they're filling up a big hole, and they can accept mildly contaminated soil. as well as other construction and demolition waste. That's including waste concrete, bricks, etc. They have a very desirable location and they receive large volumes of waste concrete, but they would like to figure out how they could reuse that recycled concrete, reuse that concrete rather than have it fill up their landfill. So they came to us and asked if we could help with that, doing that under the legislative framework in Europe. And that would help because it also meets the government's targets for recovery and recycling of waste. So the government has set some recovery goals to recycle construction and demolition waste. So this project, while it offers economic benefits, the client gets paid to take the waste, and then they could potentially turn it into a product and sell it. There's also an enormous value for them in saving the space, their what's called their void space, the empty space that they fill with waste, for waste streams that can't be recovered because they're contaminated or they have no identified use. So we all know that recycling turns waste into a product. You often probably think of things like glass and scrap metal. The European Union, of which Ireland is a member, has a recycling process laid out in legislation under the what's called the Waste Framework Directive, which sets out 4 conditions which specify when waste ceases to be waste and obtains the status of a product or a raw material. This is called the end of waste. So because there is no European-wide end of waste criteria for a waste stream like glass, European member states can establish criteria on a case-by-case basis. So we have to make an application to Ireland's Environmental Protection Agency. So waste ceases to be a waste when it has undergone recovery and it complies with these conditions, so that the substance or object is commonly used for specific purposes. So it meets it acts like a product. It has an existing market or demand. Somebody will pay money for it. The use is lawful in that the substance or object fulfills the technical requirements and meets legislation and standards applicable to products. And then the final one, which is really what this talk is about, the use will not lead to overall adverse environmental or human health impacts. So it's pretty, for something like recycled aggregates, which are used in road construction, building construction, civil engineering work, it's quite easy to demonstrate that we have a demand for aggregates. Everything around us is built with aggregates, right? The tricky one is what we call the 4th factor, what demonstrating will not lead to overall adverse environmental or human health impacts. So the end of waste process plays into the principle of the circular economy. So we are probably more familiar, well, those of us who are, as we get older, probably even more and more familiar with what we call our traditional linear economy, which takes resources out of the ground, makes products with them, uses those products. When they meet their end of life, we dispose of them in a landfill. And then we have to manage that waste in perpetuity. And we are, as I hope, as a Western society and all around the world, trying to move towards a more circular economy, which is a sustainability buzzword, but it is being mandated into legislation and best practice, where we make products and we use them and we can reuse them and recycle them through several lifespans before they go into enter what's called the waste sphere, or sort of a permanent management. So Ireland and Europe in general is looking at all of these circular economy issues quite a bit. So this project started, we have our defined problem, but we started with looking at, okay, we're not reinventing the wheel here. People use recycled concrete. They do here in the United States, they do in other countries. But what Ireland doesn't have is very, very many recycled aggregates. There was little incentive for the use of them. But it's commonly accepted in some other European member states to recycle aggregates. So this literature review looked at end of waste criteria in other European jurisdictions. So France, Austria, the Netherlands have protocols for recycled aggregates. And these recycled aggregates have to meet environmental standards to be used for construction. So these environmental standards take the form of what's called leachate limits, which I'll explain in a little bit, but it basically relates to an environmental test on the water quality when you shake this material up with some water and then you analyze the water. So these jurisdictions have, recycled aggregate systems that allow for concrete, but also brick, tile, glass, sometimes recycled stone, and asphalt, tarmac. Then we also look to our neighbor in the UK. In Ireland, we look at the UK, what the UK does a lot. So the UK has an aggregates from inert waste protocol that is basically a methodology for production. There are no leachate limits, and there is a fairly generic risk assessment, which we'll be discussing, to conclude that recycled aggregates could be used. Ireland's EPA indicated that they wanted us to see a stringent environmental approach that included risk assessment similar to those Dutch, Austrian, French criteria I discussed earlier. So what this project did is to use the tool of risk assessment to predict the environmental impact from using recycled concrete aggregates. So we use risk assessment modeling to predict environmental impact and water quality. And this allows us to demonstrate to the government and other stakeholders that the impact of the project will be acceptable or minimal or will meet the environmental objectives that have been set for this system. So it's important to remember that any model, and if you become an environmental consultant, you will use a lot of models, is a computer program that simulates reality, but it's a simplified representation of reality. So we use field measured data to represent variables. We try to model complexity. We look at scenarios that don't exist yet. We're trying to put together a computer system to tell us what might happen when we do build this thing. And so it's very important to remember that when you make a model, any kind of model, it is valid under a set of assumptions that have to be described and well understood, and also understand that that there is uncertainty. So when you're an environmental consultant, you're preparing a risk assessment, your first step is going to be assembling a conceptual site model, which uses the terminology of a source, a pathway, and a receptor to frame our understanding of the potential risks of the project. So in this image, this is maybe a nuclear site or a power plant. It has waste that's leaching, and that is the source. And that for there to be an impact on our receptor, which is, that lovely woman there swimming in the pool and her friend with the vegetables, for there to be an impact on the receptor, there has to be pathways, right? So if we don't have a pathway between the source and the receptor, we don't have an impact. But in this case, we do have pathways, right? We have contamination entering the groundwater from leachate. That groundwater, contaminated groundwater, is making a vapor that could be harmful for inhalation, or interacting with that water through drinking and bathing and swimming and using it to water your vegetables. These are all part of understanding the potential impact. So we were using a risk assessment methodology to derive what we call our end of waste criteria. So I know this is a wall of text, but essentially this paper that I reference here became our sort of, our Bible, our reference book for this project. So if waste aggregates obtain end of waste and stop being a waste, they become a product. And when I sell you a product, the only regulation on that product is relating to its specification? Does it meet the requirements of a product? So the only environmental health and safety protection for you is what is built into the requirements for that product. So when we're taking something that's risky, which is waste, and turning it into a product, we need to have restrictions and control measures to ensure that the end of waste process does not compromise the safety of the environment or human health. So that's our sort of mission statement really for this project. So the thing is that recycled concrete does carry environmental risks. It can generate alkaline, which is high pH plumes. Concrete can be used, concrete can be bound up with a variety of materials, which may include things like fly ash, which have high metal concentrations, or they could have saline sulfate rich drainage. So we started our project with generating recycled concrete aggregate samples. So these samples included recycled concrete pavements, which, like you think of your sidewalks, as well as construction and demolition waste from the demolition of concrete buildings. And some of these were generated in aggregate type processing situations where they were graded, their particle sizes were sieved out to make a common graded material. But we also had ungraded and samples, and we also had samples that were washed and samples that were unwashed. So we then subjected those recycled concrete samples to a standard European test method, which involves shaking the recycled concrete aggregate samples with water with deionized water at a ratio of 10 parts liquid to 1 part solid material. So this is a standard lab test that's used across Europe. The legislation, and the regulators the government all understands how this test works, which is I shake these up for about 3 days, then I filter the water through a filter press kind of thing, and then I analyze the water and I get chemical results for the water that is shaken off this material. The results were then compared against groundwater criteria. So, here in New York, in the United States, the EPA, the USGS, every government around the world tends to set some level of environmental criteria for their water. We call them water quality limits or criteria or environmental quality standards, EQSs. So we took our leachate results from all these different samples. We compared them against groundwater quality criteria, and we chose parameters that we were going to use for risk assessment modeling to understand the potential impact on the groundwater from recycled concrete aggregates. So these contaminants on this list, antimony, which in Ireland we say antimony, arsenic, barium, chloride, chromium, molybdenum, selenium, and sulfate. And these were chosen throughout the process based on leachate test results and also on literature review as to what could potentially leach out of recycled concrete. So our EPA wants to see these leachate limits for the final product. And the hydrogeological risk assessment methodology was used to derive these leachate limits. So hydrogeology refers to groundwater. And we used a process called impact modeling. Now this is I don't expect this is quite technical, but what we basically understand with this is we're using a sort of a relatively bespoke software that basically looks at the groundwater quality and then through back calculations of hydrogeological parameters determines what level of contamination is acceptable at the source that will not have an impact on that groundwater. So this software that we use also incorporates some probability risk assessment, Monte Carlo simulations, which means when we're running the model, we change parameters hundreds of thousands of times to look at probability values for a consideration of uncertainty and significance. So we would like, this allows us to say that we have considered the sensitivity of using this material. So this together, we use this together in a software that Golder, the company I work for, developed, called ConSim. And con means, con in this case is referring to contaminated land, and sim is, simulating. So we look at, we've looked at our leaching tests here at level 1. We have material that is leaching into water. We look at the processes that happen in the unsaturated zone, materials being uptaken by minerals, reacting with the soil. And we look at then what's happening at the groundwater level as well. There's all these processes that happen when these contaminants enter the groundwater, including dilution, dispersion. And what we're really looking to understand is the impact on a receptor. So we pick a receptor and we are trying to understand the impact on that receptor. So all that to say is, for this specific risk assessment that we did for this project, we considered the use of recycled concrete aggregates for construction of roads. And then we built 4 conceptual models using that source pathway receptor model, considering the unique characteristics of Irish hydrogeology, Irish bedrock geology. So this, I know it's very small, but this considered basically the use of this material over peat, over till, and over limestone. And the use, and then we considered our receptor was essentially a groundwater well that is 10 meters down gradient of our road. And these model scenarios represent 98% of Irish aquifers. And this final, the one on the bottom right, scenario D, which is just limestone, is considered the most vulnerable geological setting because it's limestone only with no superficial deposits over it. Those superficial deposits like soil, peat, till, clay, they all have processes that help to mitigate contamination. So going straight into limestone is considered the most vulnerable scenario. So long story short, we run all this through a model, and this gives us, for our 4 scenarios, a maximum concentration that is allowable at the source. So the stuff that leaches into the groundwater, it leaches into that leachate sample. And then using, sorry, that text box got a bit lost. Using literature values, we can convert those maximum modeled concentrations back to a limit value for that leachate test I was mentioning earlier, that 10 liquid solid ratio of 10 to 1. So that would allow our client to take a sample of recycled concrete aggregate, subject it to this leachate test, and see whether it passes or fails. Essentially, we now have a limit value. So that value from literature is known as a kappa, which is specific to, which is a specific value that it relates to the liquid to solid ratio for the proposed for this type of test. So the most conservative maximum concentration was chosen from the 4 scenarios, and those were proposed to Ireland's Environmental Protection Agency as leachate limits. So we as a courtesy to the EPA, we compared them with other European criteria. In some cases, our limits are a little bit higher. In some cases, they're a little bit more conservative. But the important thing is that we have specifically considered our unique geological environment. We're not the Netherlands, Austria, or France. This is Ireland, and so this is what we proposed. And so all that work was around demonstrating no environmental impact, but we still have other conditions, right? We also have to demonstrate that it doesn't cause harm to human health. And we also have to demonstrate that it can be manufactured in accordance with the technical specifications of a construction product. So we did some human health risk assessment. That's not my area, but essentially we did that similar process of looking at a conceptual site model of workers, construction workers, people interacting with this product. And the fact that it's buried under a road and it's being used in roadway construction meant that there was no additional requirements for the construction industry compared to any other aggregate product like a generated from virgin limestone in a quarry. And then we prepared a quality protocol, which is say, how are we going to manufacture this, right? How, and this involves, this is essentially how to make aggregate, which is, you know, something that happens all around the world, but there are additional requirements because this material is being recovered from waste. There are more stringent requirements for the production of this material to ensure that it's not contaminated with waste. This includes specialized testing to make sure that it doesn't contain metal, plasterboard, gypsum drywall type material, things like that. And also that leachate testing that we referenced. So this quality assurance program has to comply with European standards for aggregates, but that just like a quarry making a virgin product would have to do as well. So the final submission resulted in a grant of end of waste criteria from the EPA. And a number, as we discussed, we have to have restrictions and limitations to ensure that this is highly protective of the environment. So some of these restrictions and limitations included that this material could only be used for roads. So when our client sells it, they have to tell people you can only use this in a road construction. And the reason is that's what we modeled. It can't be used in direct contact with ground or surface water, and that's because of the risk of high pH alkaline plumes from concrete. We've established our leachate limits. We also have limits for hydrocarbon contamination. That uses, the slide uses the term mineral oil, which is a bit of an outdated term, but that is still used in legislation in terms of the amount of hydrocarbon that is acceptable in a material. And then it has limits on physical parameters, as I discussed. And that it's very important to remember that for our client, they were given permission for this, and they have to do it under authorization, which means they have a license from the Environmental Protection Agency to do this recovery exercise, and it has to meet the specification. And that recognizes that the recovery of a product from waste requires robust management and regulatory oversight. Not everybody can just go about recycling. It needs to be done in accordance with the legislation. And our client, one of the ways our client did that is they also established, they became accredited. So they're producing aggregates that are accredited under a statutory body. So if we review our conditions, we can see that together with risk assessment and the quality protocol, we can demonstrate the recycled concrete aggregates meet the conditions of end of waste. Aggregates are commonly used for specific purposes. Demand exists for them. With engineering controls, they can meet the technical requirements for legislation, under legislation for the product that they represent, and that the use of the substance or object will not lead to overall adverse environmental or human health impacts. And although this aspect is still being quantified, actually I should say, since I wrote this presentation, our client has had this quantified in terms of the carbon value of recycling aggregates. There is a significant environmental impact of disposing of concrete rather than reusing it. When you consider the alternative of taking a virgin rock, crushing it up, using it and disposing it of landfill, and then sourcing more virgin limestone material for more aggregates when you need them, the sustainability benefits are huge, because you have both the landfill aspect and you have the utilizing of extremely precious natural resources to generate virgin aggregates, which can be controversial. You know, some people don't like living next to gravel pits. And so the end of waste ties into the circular economy, and altogether, this project can be used, I think, is an interesting way of understanding how we can make decisions about recycling and reuse in a really holistic framework. And I think it's interesting to talk about, I mean, you know, concrete aggregates are not the only area of application. You know, here in recycled concrete is used here in the United States for road construction and other uses. We can also, there's also applications of recycled industrial waste for, you know, like example, using crushed glass to rather than pebble and sand in concrete. You can also generate recycled natural aggregates from soil washing. So if you have contaminated soil, you can wash out the contamination, which tends to sit in the fines. It sits in the clay material of the soil. And so then that's about 20 to 30% of the soil. You can landfill that, and then the 70% that's left can be recycled as aggregates with, you know, at the sand all the way up to stone sizes. We have some clients looking at that now. Waste wood can be used for biofuels. We have a client who has an end of waste decision for industrial byproducts and ammonium sulfate that comes from the manufacturing of computer chips that they're using for fertilizer. And another one I think is really interesting here that they're doing in Germany. And I saw there's a company in Vermont doing, it's called Glavel. It's a glass, it's a foamed glass that they're using as aggregate. And there's a company in Vermont doing that. So, and then another one I didn't mention, I have a picture of, but not the words, is road planings, you know, asphalt. When we strip off the road, reusing that asphalt in a hot asphalt plant and turning it back out to repave roads. And in sort of the other area of mining, other area of consulting that I do, which is mining, we often do this kind of work to get permission to use mine waste rock for construction. And that's really an end of waste process. We go through these leach tests and environmental tests to demonstrate that the material won't cause impact or won't cause an unacceptable impact, including risk assessment. And then we go to the regulator and say, you know, our client's going to be mining out this rock, this waste rock that they won't be getting metals out of. Can they use it, you know, to lay down a pad for their roads, or use it in construction of their, you know, their environmental dams or berms? So there's a lot of applications for end of waste, and I think it's a very interesting and challenging area to work in. And this is a picture of my client's landfill at dawn, looking out over that little island there. Is called Ireland's Eye, right there. And this was it. I was there at dawn to supervise the mediation project anyway, and it's a really beautiful spot. I say it's the prettiest landfill in Ireland. And thank you so much for your time and attention. And thank you very much. Yeah. Let me just open the Zoom. Where did it go? I just minimized it, but it's not maximizing. Did I lose it? What's that? Because I just hit the minimize button. Oh, yeah. No, I will not. I won't even touch anything. I just want to see. Okay, is there any questions in the room? Yes, Michelle. Yeah. Yeah, I know I actually don't really think that the test method that we use, I don't actually really like the test method at all. And Europe is quite insistent on it. And I don't think in the US we have the SPLP test, which uses a mildly acidic, more like a rainwater, which I think is a better test. I don't think this is the best test, but it's really at this stage what's understandable, yeah, to the regulator. I think the issue is that if you're using like a simulated rainwater or things like that, they can contribute alkalinity, which can have a significant interaction with the sample. So I think, yeah, I know it's not great, but it sort of is what is acceptable, unfortunately. Yes, Fred.
So that fourth rule says something like
Yeah.
So does that mean can that be interpreted aggregate, right? When you have things that you can't compare.
Yeah.
How do you determine the net?
Yeah, sorry, I forgot to repeat Michelle's question earlier, which was about the leachate test, and then I'll repeat Fred's question now. Fred is asking about the terminology of overall adverse environmental impact, where sometimes you're not comparing, you know, like for like is the offset on carbon credits enough that it justifies slightly more contamination or something like that, and it's a very interesting wording, and people do argue about it a lot. And one way that Europe has dealt with it is what's called the comparator test. So on purely just a basis of those leachate limits we talked about, if you can demonstrate that the leachate is similar to the leachate from a virgin aggregate product, then that can be an argument, and you don't have to go do all that hydrogeological risk assessment that I just did. And as I was saying with over in the UK, where they've decided that they don't require risk assessment and they will allow recycled aggregates as long as they're done in accordance with technical specification, that essentially is a decision that the reuse is more valuable than any sort of level of mild contamination that comes from the reuse of those products. So it is dealt with in different ways, and it really just depends on the jurisdiction and the regulator decision as to what sort of risk tolerance they're willing to accept. But it has been, it's very interesting wording, because really, yeah, the environmental impact of disposal is so huge, you know, that we really should be accepting, you know, a more sustainable reuse scenarios. Any other questions? I didn't, please, if you'd like to ask any questions on Zoom, please feel free, anyone. Yeah, and if not, we'll wrap up there, and thank you so much for listening.
Okay, thank you very much, Martha. We've got one more talk next week before Thanksgiving. One more talk next week before Thanksgiving. It'll be Elena Geisha, also someone who grew up in Alfred, who will be talking about climate change. And she is now a assistant professor at Colby College. So that'll be completely on Zoom. She will not be here in person. Coming from Maine was too far. Martha came from Ireland, but she can't come from Maine. I don't know. No, Martha was coming anyway. So, all right. Thank you very much. And thank you, Martha.